fact, I just bumped into somebody in the hallway earlier, and we ended up talking about it, and he had a very different perspective on the whole talk than I did. That just happens because we had a collective experience and we're walking around.
Hey everyone, thank you for joining here today. We're gonna speak about, we're gonna speak about using coroutines to implement C++ exceptions for freestanding environment. So, ever since I arrived here in CppCon, I keep hearing, that exceptions are for the exceptional. How much time did you hear this? How many times did you hear this? Yeah, say some nods in the audience. So that means that maybe exceptions are not for everybody. And if you want to get convinced by that, just go back and remember Bjarne's opening keynote where he said, hey, so when I introduced exceptions, I didn't mean that this would replace every other error handling. It's not appropriate to use exceptions just anywhere where you want to just handle errors. But you know something? Still discussing with all of you in conversations, I keep hearing great stuff. I keep hearing that you have crazy programs that you developed. Some of them are actually spaceship-related programs. I heard at least one example of that. And you were telling me about this case where you actually had to take your program and you recognize some kind of hot path, and it gets hit all the time, This hot path gets hit all the time, and it almost never fails. And you actually were able to benefit in performance while using exceptions because you avoided the runtime cost of checking the errors at the call site every time. This, to me, is super exceptional. I mean, just this morning, we heard Michael's talk, like the inspirational talk, and he talked about freestanding, and he said, there are so many embedded software out there. There's so many embedded processors out there. And most of you who attended also raised their hand when he asked who is doing embedded here. Heck, he even mentioned that the giant thing above your stoves has like an embedded processor in it. So how cool is that? So what does it mean? Does it mean that we can't use exceptions in those environments? Does it mean that exceptions don't belong to all of us? Just take a look at this code. Oh, this was so long time before I showed the code slide. I feel like the oxygen is getting back to me. So in this code, you can see that it would almost not fit the slide if I had to use just plain error codes instead of exceptions. And this code is only taking a file, opening the file, and mapping it to memory and using the file. So what does it mean? Does it mean that this code is exceptional enough to use exceptions? Well, according to a talk that has been here this week, a talk about error handling by Robert, I think. So he said that you can't really know. This is a library code. Somebody else might use it and in a spaceship program, And maybe what they're trying to do is open a file and check if it is of a specific format. And most of the time, it is not in that format. So what can you do about this? So do we not get to write code like this? What about all these giant stoves about stove air sucker above your stoves, right? So what do we do about this? We need to fix this code. We need to fix this code. How are we going to fix this code? We're going to make this code exceptionless. But not only that, we're going to have no additional lines added to the code. We're going to have no RTTI. And remember, from Michael's talk today, he said that the first thing you want to do for embedded is disable exceptions and RTTI. That's not me saying that. We're going to have less than 10 changes. We're going to have no macros, and it's going to be zero overhead. The best part, is not the zero overhead part. The best part is it's gonna run without runtime support. No C++ runtime support. I mean, you do get to write the standard C++ that we all love, like C++20, we all love it. But you don't have to link with the library. I mean, if you use the appropriate compiled flags that I can give you, it's gonna be also in the appendix of this presentation if I get there. If you do that, you don't need to link with the C++ runtime. How amazing is that? So, who I am. My name is Eyal Zedaka. In Hebrew, you say it like Eyal Zedaka. It's like kind of different thing. So I do a lot of C++, operating systems, low level, and software security. Most of that I actually do in Magic Leap, where I work. Magic Leap is an augmented reality company that develops amazing augmented reality glasses. You should come meet me after the talk to get some videos if you want to see. It's truly amazing. I do C++ lectures from time to time on invite basis. I do some open source. I really like, as I said, I like operating systems, so you're not surprised to find a hypervisor there. And I also like Vim, so if you are crazy about Vim setups, go meet me after the talk as well. And I will be glad to meet you as well. So let's get back to topic here. So C++, you know, this sentence gets been said all the time. Like it is said almost in every inspirational talk that I've been to this conference. C++ is the zero overhead abstraction language. What does this mean? This means that we need to be able, so let me phrase it otherwise. We better be able to afford the abstractions, right? Because they're supposed to be zero overhead. But what about exceptions? Exceptions, they are providing abstraction. Most of us think of exceptions like it's some kind of implementation that you're supposed to use only when you succeed or only when you have like these spaceship programs that I mentioned earlier. But it turns out, the way I think of it, exceptions are just an abstraction. It is not supposed to be bound to a particular implementation. There are actually related papers on the topic. One of them is discussing, like by Herb, one of them is discussing implementing static exceptions. And there is one by James Renwick, which is discussing taking the existing exceptions and just providing another implementation that is possibly ABI breaking. And we all know what when we're gonna get an ABI breaking feature. So these kind of things are being discussed. But in this presentation, we're not gonna do any papers. We're gonna discuss only C++20, only standard C++20. And boy, we're gonna do it while leaving no room for a lower level language. This is all the things that I used to work on. Like this is just what I used to work on. Maybe you guys are working also on stoves or spaceships, you know? And you can't use exceptions, but in any of these cases, I'm telling you, you will be able to use this solution. So let's do some overview. Of course, we're gonna use coroutines in the talk, that's in the title, and we're gonna start with some ramp up to kind of get everybody on the same page. And it will be very quick, so just pay attention. If you don't understand something, please ask. If you have like extra bonus questions, you may ask that during the end. And so we're just gonna show a code example there, and we'll just discuss the support types required. What do you need to compile this example? We're then going to talk about the design and implementation of this library, and we'll iterate it. I'm not going to give you the solution right away. We're going to iterate it, so okay, until we get to the right solution. And we finalize by summarizing what we achieved. There may or may not be an extra surprise. Let's see how we do on time, and we'll get back to you on that. Okay, so using the library. So the example that has to fit the slide here is commonly used in this conference. Let's divide some integers, right? So how do we divide integers? So here is how we do it in this library. You can easily see the differences between just this code example and what you would do when you normally use the exceptions. So the first thing you want to do, because we use coroutines, is to return this throwing of int type. And as we get this x and y, we're performing a check to see if we're dividing by 0, and then we yield. There's not a throw. It looks like a throw, but it is yielding. So next, if you want to return, actually, right? So do you just use co-return? These are standard keywords in C++20. And you can see that we have an extra check there in the middle that is doing like a check if the result would fit an integer, if this is like a whole number. So how are we calling this? So this is a way to call the function. Instead of just calling the function and just getting the throwing type, I want to actually get the integer out of it. So the way to do it is using this co-await. And as you use this co-await behind the scenes, it will check for errors and it will propagate for you, and we will see that. How are we catching the exception? So here is a nice function that is super heavy on metaprogramming. It looks very similar to std_visit, but what it really does is just take this function object at the beginning, executing this function object, and finally, if we get an exception, it's gonna try and fit that exception with one of the catch clauses. I call it catch clause, even though it's just a lambda, but it looks similar, right? So it's going to call one of these catch clauses. So how does it know? I told you that we're doing no RTTI. That's a good bonus topic that I'll point you in the GitHub to look at, but we're not gonna cover this today. So, coroutines, what are coroutines really? If you haven't seen coroutines in the past, coroutines are really just functions. And those functions support suspending and resuming. What does it mean, suspending and resuming? Imagine that you are writing just a normal function. In that normal function, if you would want to suspend it in the middle, what you would do is cause some suspend to occur in this coroutine and just return. It would just be translated to a return. So anytime I want to say the coroutine is suspended, the coroutine behind the scenes really just inserts a return, and after the state of the local variables are stored in some kind of thing that's called the coroutine frame. So you could imagine coroutines as just being like a normal function with this allocated coroutine frame. All your local variables are there, and suspend is simply a return. Suspend is just a return. Remember this. This is not like suspending threads. It often confuses people, so I want to make sure everybody understands that suspending is returning. So how do we resume? So if we need to resume, we just call another function, pass the function this coroutine frame, and the coroutine frame is gonna tell the function where to resume from. It's gonna be like a switch case. The switch case will just check inside the coroutine frame, where did I stop? And it's gonna tell it you stopped at state number 4. So in case state number 4, what it's gonna do, it's gonna pull the needed local variables from the coroutine frame and just continue executing. You could do it yourself, I mean, with a struct or something, but coroutines are really providing a nice syntax for that. And to me, they're just reducing complexity. So here is our code. If I were to take this code and Godbolt it, right? I put it in Godbolt. What would happen is that Godbolt will start to throw some errors on me and tell me, hey, you have a bunch of things unimplemented. But slowly, it will start holding your hand and it will tell you, hey, you are missing the declaration of this throwing type. And then it will start telling you, you're missing declaration of this function and this function. And eventually you get to something like this. It's not really, it's big, but it's not really scary when you think of it. You don't have to remember any single line of this. You just put it in Godbolt and Godbolt will tell you the truth. It will show you the way, okay? So what does this thing do? So first thing you want to take a look at is the promise type. The promise type is kind of where you store the state of what you're promising to the user. So you can imagine that in our implementation, we will just put there the result of executing the coroutine. Did it throw an exception? Did it succeed? So that's where we're gonna store the result. Outside of it, we have the throwing type, which is the awaitable object. And this object, it's gonna be used in a way that every time you use co-await, it's gonna check, did we succeed? And did we succeed is just the await ready right there. It's gonna return true if we have a value inside the promise type. When does it return false? If we have an exception. If there is an exception, we return false. Now the cool thing about coroutines, because they are designed for asynchronous programming, this ready right there, if it's not ready, what's supposed to happen in asynchronous programming? It's supposed to call suspend. And this is how we're gonna exploit it to propagate the errors, using this very suspend. In the end, it's gonna, if you succeed, I mean, it's gonna be ready, and it's gonna just return what you returned. It's gonna return your return value. So let's just take a look step by step. First thing, you want to call the getReturn object. This getReturn object is really the factory function for the throwing type. It's just supposed to construct the throwing type and return it. Next is yield. Every time you yield, the only thing that happens is you call yield value. Now notice this yield value is returning suspend always. This means, remember, we said suspend is just return. Every time you see a suspend, you're just going to return from the function. And this is what we want because we implement exceptions, so we really want to exit the function. Next is the return, but the return doesn't return any kind of suspending. Following the return, there is usually a call to this, I'll just say it verbally. There is a call to the final suspend, and the final suspend will tell you, hey, do you want to really pause the function right now and just return, not destroy the promise? And the answer for us is yes, because we want to inspect what happens in the promise type just a minute before we free all the coroutine state. As I said, this gets called when you co-await. So it's going to really ask, is there an error, is there a value? And then it's going to suspend or just resume, like call or wait resume, in which case the execution is not changed. This is what I just said, so I'm going to skip it. And finally, the coroutine handle is what lets you control the execution of the coroutine. Do you suspend the coroutine? Do you resume? Do you destroy? So it doesn't let you control the suspension, but it does let you resume and destroy, and of course to invoke it. And here is how it's gonna work behind the scenes. So if this was too complicated, this is the chance to really get a good understanding of what's going on. So let's say that we succeeded. So if we succeeded, we get to the return, right? So we're trying to return something, and we invoke the return value, and then we invoke the final suspend. The final suspend, remember, it has to suspend so we can get what happened. So when we suspend, it's just a return to the caller. After we return to the caller, what happens is that the caller is awaiting the result, and then it's able to understand that there is really just a value there because we returned the value. Now await ready is true. Everything is good. We succeeded. Okay? Now, when we get to the failure path, it's a little bit different, but very similar. We now have to call the yield value. And the yield value is really just inside the promise type is going to store the exception that we are yielding here. Similar to before, we get a suspend and we go back to the caller, but this time we're really trying to co-await something with an error. And that is where we suspend the caller as well. And we get to its caller, which gets to its caller until we really get to the try catch where we inspect what we just have. So I want to pause a little bit and analyze what's going on, because to me, like as an embedded software programmer and a security programmer, I want to understand what happens in the assembly. Now, you will need to follow my lead there, because I don't want you looking at all the assembly. I want you to just look at what I want you to look at. Okay, so just follow my lead and you will be okay. All right, so this is the assembly. This is, of course, using Compiler Explorer. Thank you, Matt Godbolt. And here we can see a few things that are very interesting. The first thing we're going to see is that there is a memory allocation, which is really bad if you just divide integers. So we don't want that memory allocation. Another thing is that inside that memory allocation, the compiler, this is Clang, the compiler stores this resume and destroy functions that you can see. Maybe I can just highlight it for you. You can see this gets stored inside the, I want to call this the coroutine frame allocation right there. I will just call it the coroutine frame. So inside the coroutine frame are the pointers to those functions. Later on, we're going to get to the return object point. And the return object is, again, constructing our throwing type, and then it immediately returns. Why does it return? Can anybody tell me why there is a return here and we're not doing anything? The reason is that initial suspend is suspending. It's returning suspend always, and that's why there is a return. Maybe we can optimize it and start executing the function before we return, right? So you can think about that. So if we go to the resume part, because we haven't done anything yet, we need to do some execution of the coroutine body, right? So this is where the resume function comes into play. And this is really what happens here. The first thing is that you don't get the parameters anymore. The parameters are in the frame. The frame pointer is RDI. And it is just checking where should I resume from. Do you see this compare AL stuff and then jump? This is just a switch case. Hey, where should I resume from? So if I just executed the entry function from before, it will have to resume from here, from the are we dividing by 0? Okay, are we dividing by 0? If yes, it's gonna go to yield value divide by 0. If no, it's gonna continue and compute the x over y, and then it's gonna check the remainder. Is the remainder 0? If the remainder is not 0, the result couldn't fit the integer, so we get to that point. But if it is, we're just gonna return a value. And notice the final suspend that happens after, and final suspend returns suspend always, and that's why the compiler just returns. Okay, again, there is just a return. So we finished what we wanted to do. There are two more interesting functions. One is the cleanup function, and one is the destroy function. The first one is the destroy, the second one is the cleanup. What's the difference? They both kind of call the destructors of the local members, like the local variables that you had that are kind of members if you think about it this way. But there is one difference. And the difference is coming from this deletion right here. And one, which is the destroy, is also deallocating memory for the coroutine frame data, okay, the frame object. This is kind of leaving, like if you've never seen coroutine code before, this is leaving you wonder, hey, why do I need these two functions? Perhaps the second function, the cleanup one, is leaving room for the compiler to get rid of the allocation. So what did we just see? Okay, we have two issues that just by looking at the assembly, I have to kind of share these two issues with you. We have 240 lines of code, and it's running with O2, it's with optimizations. We haven't implemented anything yet. I was just showing you that the type that I showed before, there's no function implementation for nothing, so that's why we didn't see much inlining, but it's still big. The second thing is that we see the dynamic memory allocation, which is just unacceptable. I promised you 0 override, and now I'm showing you dynamic allocation. Okay, so you're gonna fire me after this. So let's focus on one thing at a time, right? So the first thing we wanna focus on is let's implement this throwing of t, and maybe the compiler will see what's going on, and then the compiler will replace our program with a better program which does something else, right? Which is doing the same thing, but is achieving it in another way. So here's the implementation, and this is like the fully declared or defined throwing type, and we're just gonna go one by one, and we'll see that it's very, very simple. So first thing is that there is an exit condition right there. This exit condition, you can think of it as if it was a std variant with some optimizations, because we don't need a full-blown variant. And it's gonna just store an error or a value. That's about it. That's our promise. And below, there is like the coroutine handle. And this coroutine handle is again, what's controlling the coroutines. It's also pointing some kind of to the promise type. So it turns out that in order to construct this throwing object, all we need to do is call like a standard library utility that would get us the coroutine handle from the promise type. This is pretty standard. That's like a one-liner code. Next, we do this optimization that I told you before. We're not gonna actually suspend when we initially execute the function. The function is gonna start executing, and it's gonna reach either a yield or a return, one of these. And final suspend, we have to suspend to just take a chance to look at the exit condition. We're going to yield and return values. I'm not gonna show it because it's just gonna call functions of the exit condition and store it inside. Of course, yield suspends because we don't want to continue executing after we just threw an exception. And this is just standard move constructor. It's just like pointer type move constructor. And when we distract, we want to destroy the coroutine frame. And finally, this is just kind of an abstraction there that is checking await ready. It's just if we have a value. Await resume returns the value. Await suspend is propagating there. Now this is like a different thing. Since we already know that there is no value in there, we can implement like a very smart error propagate that maybe it is just doing a mem copy. Okay. So let's see.
Where do you store the lambdas?
Where do I store the lambdas? That's in the try catch. That's a good question for after. I didn't want to focus on the try catch because it's just this million lines of meta-programming code, but it's a valid question.
Where do you store the exception?
Where do I store the exception? In the exit condition. Okay, very good questions. How does the code look like now? Now we've implemented anything, so the compiler can inline everything, right? So here is a full program this time. This time we have a main function, because we can link now. And this main function is just going to check if 4 over 3 equals 2. Of course, this is not true, but not only it is not true, it is also not an integer. Okay, so that's why we're going to reach this range error kind of thing, which returns 4. So we are expecting the program to return 4, right? Let's see. Here's the program. It returns 4. So it worked, but we still have a lot of assembly. This is about 400 lines of assembly, and it's not very pretty. So what are we going to do about it? An additional kind of slide of the assembly. The integer divide even did not get inlined. So there's no inlining, and this is how it looks. It still allocates the coroutine frame. You see this operator new? Still allocation of the coroutine frame. Notice that you can know that this is the coroutine frame just because here the resume and historia is stored inside the coroutine frame. So that's how you know that is the frame. So we need to talk a little bit. I need to show you some simplified view, which may not be accurate, of what's going on behind the scenes. And this simplified view, it will help you understand how to control this memory allocation of the coroutine. If you want to kind of get rid of memory allocation, this is what we need to learn to be able to do it. So the example function here is a coroutine, and it has some body. You just kind of optimized it out for you. And this is how it looks. Now, this may be the only complicated slide I have here, but it's really the simplified form. I got rid of the destroy function. It's really, really simple. I'm just trying to kind of show you what we can do with it. So notice that here we have the frame like constructions and allocation. And this frame allocation is also where we kind of store the promise type and construct it there with the placement new. After this, we get the return object, and then we kind of start the initial suspend ceremony and executing the coroutine body, and the final suspend, cleanup, delete ceremony of just getting rid of the coroutine. Remember, final suspend in our case is suspending, initial suspend in our case is not suspending. This part is where the call site is kind of doing the co-await. So this co-await is just gonna check, hey, are we ready? If we're ready, if we're not ready actually, because there's an exclamation mark there. If we're not ready, it's gonna suspend. And if we are ready, it's gonna resume and get the result back. And this is what you need to focus on. These are 3 things here, the new and the 2 deletes there. By the way, this resume function right here is just like after you've executed the entry function, you remember you don't need the parameters anymore, so you resume on the frame. And this is where you continue to execute the coroutine body and just do the cleanup finally. There's also potential suspend from this point, so just pay attention to that. So these are the things that we need to know. We need to know just the new and the delete right there. But what happens? Can you ask that in the end of the slide? Just a few minutes.
All right.
Yeah, Yeah, once the bottom line turns blue, you will be able to know it. So it's the end of the slide. Okay, so thank you for that, though. Okay, so here, just take a look at this initial suspend, and I'm telling you, this is the key to optimizing the allocation out. Right now, we're returning suspend never because we want to optimize. We don't want to pay for an additional suspend, right? But you know what? Let's do something very stupid. Let's pay for the suspend. I paid. Here, take my money. Okay? So what happens now? Remember what I told you in the beginning? Suspend means return. So what happens here? The compiler is just getting rid of the code. We just return. Okay? So once we return from here, this code that is calling the coroutine entry function, it looks like it's calling a very, very small function now. Okay? And the compiler is going to inline it. Okay? This is the key part for getting this optimization. Once the compiler inlines it, we can do the same thing everywhere else, right? And of course, the destructor is really small. It's just calling one function, so it also gets inlined. And look at this. We just mated this new and delete, right? They're now mated. So every time you new and you allocate the coroutine frame, you're gonna delete it. There's no matter what. It is even in the same expression. It's not even a function. Remember, it's just all coming from the co-await. So this is what is being done. Did you see that? It's just delete it, put it on the stack. Okay? So once we do this, did we finish? You want to think about this for a few seconds? We did not. What is missing here? Who is executing the body of the coroutine? So nobody. The answer is that we just did something. We did some dance. Nobody now executing our code. So nothing works. How do we solve it? Let's just, there is an await ready there. Why don't we just, before I tell you if I'm ready or not, let me just go execute this function, and then get you the result back. And that's exactly what we do. Await ready is going to resume the coroutine, execute the coroutine body. The coroutine body is going to either return or yield, and then we're going to know if it's ready or not. If it yields, it's going to throw an exception, so we don't want to be ready. I want to suspend it, propagate it. But if it's ready, we just return the value. This is a nice dance, right? So how does the output look now? Do we get this frame allocation elision? We do. And let me show this to you a little bit bigger. There it is, and there is your proof, actually. Now the resume, and now there is a cleanup. Remember, the destroy is deleting, the cleanup is not deallocating, right? So here is your proof. We moved these pointers to the stack, to RSP. That means we just got rid of the allocation. But here is another interesting thing. If you weren't able to figure it out, we also immediately call the resume. Because we've inlined the entry function, now all we need to do is call the resume function. So we make the stack for the resume function, then we call the resume function. It's still not like the kind of thing that will convince you, oh, the code is good enough, but it's, it's step by step here. We're not going to give you the solution right away. Okay? So, yeah, that's what I said. So here is, you wanted to ask a question before. Did I answer the question?
The dollar signs are still in there, right?
The dollar sign is just a pseudocode. I mean, it's not really actual code. Yeah. Yeah. So, yeah, you maybe can see that in the assembly, like this dollar sign, but it's kind of the pseudo kind of thing. Okay, so let's talk about what we just did. So did we resolve something? So we resolved the memory allocation, and now there is no memory allocation. It is super reliable. But we didn't resolve the amount of assembly. If you were able to see, the assembly still doesn't look good. But we just got ourselves a new issue, and this issue of, hey, but I just showed you that you have to have the function defined before you get this memory allocation vision. How otherwise could you inline the entry function? You couldn't. So we'll talk about that, but let's now focus just on the assembly. Let's get the assembly better, okay? So here is how we get the assembly better. Just look at this function. This is the exact integer divide from before, but if you look closely, there is two things that we didn't mean to do. When we yield, how the compiler looks at it is like, hey, let me just yield some value and you can return here later. It means the compiler is generating the code after the yield so that we could resume it. Now, this could be a nice error handling approach to just, you throw an exception, then you resume from where you thrown the exception, but we don't want to do that. So let's make the compiler happy. So how we make the compiler happy? Here's an attempt. We just have this special suspend no return kind of type, and we just return it from await resume so that the compiler knows anytime I'm inserting an await resume, it's just no return. So there's no point in generating this code. And this works, but it's still something that we can do better. It works, I mean, it gets rid of most of the assembly, but it's not getting us where we want to be. This is getting us where we want to be, okay? This is, instead of yielding, we just do, again, something very stupid. We just return, and then by returning, now the compiler is sure that, hey, there's no resuming from return. So this was a nice trick, and this would get you to actually need to define a different return value function, which will just check with if const expr, hey, am I failing or not? And then it will get you to kind of where you want to be. And let's look at the assembly of this example. Here is the assembly. It's a pretty small, but let me tell you this. Let me just see if I can magnify this. This is 59 lines of assembly. We came to this from about 400 lines. So let me make it a bit larger, 59 lines. This is impressive. But where is our coroutine? Where is the frame? Where is, like, do you see anything? Do you see any coroutine here? So there is no coroutine. The coroutine got completely eliminated, and we got real assembly code that is throwing exceptions. How amazing is that? I didn't tell you one hack that I did, though. Can you look at this inline threshold kind of thing? We need to help the compiler to get to this point. I mean, we did all of these things, but we had to just push the compiler a little bit further to be able to get this true assembly code. Yes?
Was there anywhere that you might have been able to put always in line or first in line or something that could have avoided that?
Question was, could I put force in line? That's a very good question, and the answer is yes, but I mean, this is not where we're stopping. So let's continue, and then we'll see if we need it. So we just resolved the issue of the large assembly, but we have a new issue that now the syntax is looking like you're just returning a value where you're just throwing exception, and it doesn't look very good to me. I mean, I want to be a little bit more, generate a little bit better program, you know? So we're also relying on this inline threshold, which is a problem, and we still didn't resolve the cross-translation units. I'm kind of messing with you, and I didn't still resolve it. So let's see what can we do to do the translation unit kind of thing. So here is a translation unit A and translation unit B, and translation unit B is defining this example. So there is no way the compiler, without link time optimizations, I mean, just understand that the coroutine entry could be inlined. So there's no way the compiler can do that. So how can we resolve it? Maybe we do something like this. So remember that the coroutine is really like a property, like an implementation property of the function. You can't know just by the function declaration if it's a coroutine or not. You have to look at the implementation. And in this particular case, the new example that we just defined is not a coroutine because there is no co-wait, there is no co-return, there is no co-something in there. So it's not a coroutine. But the lambda inside, it is a coroutine. I'm not showing the syntax here, I'm just showing the pseudocode of the frame allocation. But does that resolve the issue? The answer is no. It doesn't resolve the issue. Because even though the compiler could inline the entry function of the lambda, where do we destroy this like coroutine? We are destroying this in translation unit A because we have a move constructor that is taking the throwing type outside. Maybe this is even elided. And eventually we reach the translation unit A where the actual deallocation happens. So there is no way the compiler could optimize it and get rid of the coroutine frame. Here is an attempt of how you could do it. And this is just having another type, just store this exit condition right there. And this type will actually be returned. So the coroutine frame gets destroyed, this type gets returned. I mean, we can do these types of dances, but we don't really want to write code like this, right? So let's do something better. So just because, you know, this got me inspired, just this exit condition right there. Why do I need another type like exit condition? Why do I need something like that? Let's make the throwing type have the exit condition, right? Just check this out. The throwing type now has the exit condition, so there is no coroutine handle anywhere. And our promise type is almost meaningless. It's just pointing to the throwing type. Check this out. We're constructing the throwing type. Here is and then the throwing type gets constructed. And we just assign this pointer in the promise type. So now the promise type knows where the throwing type is. And anytime we yield a value, it's going to directly go to the throwing type. Any operation on the promise type is now becoming an operation on the throwing type. And this is really helping us to work across translation units. And I'll show a little bit more about what happens here. Notice this suspend never. Now we don't need to suspend anywhere because everything is in the throwing type. We don't need to suspend just before just to get the data from the promise type. It's all in the throwing type. Notice this yield value. This yield value is like the no return yield value. What it's doing is just, I call this suspend destroy. Imagine like somebody calls your function, you return a bomb out of the function. And this bomb is gonna, every time you suspend, is gonna destroy you. Look at this. I'm returning a bomb and it destroys the caller, right? So what this bomb is doing, it is letting the compiler know that every time I suspend, every time you suspend, the coroutine gets destroyed. So that means when you return, because we have suspend never, you're going to destroy. When you yield, you're going to destroy. So all the time you're going to destroy. And when the compiler sees a function that you have a memory allocation, at the end you destroy, it's just going to elide the allocation. No question in that. And now we don't even need inlining to achieve that. This is just a normal function. You delete, it's getting elided. So again, we do this is value to check if there is a value. We return the value. And again, every suspend is a destroy. So here we propagate the error, but afterwards we destroy to let the compiler know, hey, every suspend is destroying the coroutine, so you can elide any coroutine allocations. This design is also very nice. So if you do the exit condition well, you're gonna achieve something like 2 of size of pointer, and we'll see what else we can do with that exit condition later on. Okay, so let's compile this. So here is the result, and let me spoiler alert for you. This is just the same 59 lines, but now, Jason, now we're not doing inline threshold. No force inline. So we just resolved all the problems that I mentioned to you since the beginning of the talk, and we did a few things. Now we're working across translation units. We now use the yield keyword, which is the bomb kind of yield, which is destroying you. And we got rid of the inline threshold. How good is that? Look, I'm not going to show in CppCon like integer division that is 59 lines of assembly. There's just no way. I mean, this is just not good enough, right? I'm sure that all these embedded people or the giant stoves that are running these processors are not going to fit like 59 lines, yeah? So just pay attention to this code here, okay? So this is the regular code that we had, and I want to show something, so look closely. I'm going to change this code in a moment. Did you see what happened? Just look at this integer divide right now. What is it doing? Instead of throwing a dynamic exception, why don't we just throw like an enum, right? An enumeration type. And it turns out you can do it with any enumeration type. But here I just chose this std_rc. So if you use this library, you will be able to use whatever you want, okay? So check out the catch clause for this. It's just catching std_rc. And if the result is out of range, it's going to return 6. So what is this code supposed to return? Anybody wants to guess what's the return value here? 6, right? Because the result is not an integer. Before it returned 4 because we threw a dynamic exception, but here it just returns 6. How many instructions? I said less than 59, so do we get less than 40 instructions? There's just one instruction. And if you exclude the return there, which is like every main function has a return, there's just one instruction is going to do that for you and return 6. But there's kind of a few lies here, right? Because I just provided constants, so of course it returns 6. The compiler can just say, oh, you know what? I know what you're going to do, so here's a program that returns 6 and goodbye. Okay, this is not convincing. Let's look at what happens if we change x, y, z, right? This time, we get a little bit of assembly, but this is true assembly that is doing integer division safely. This is like real assembly. There's no coroutine in there. Anybody can afford this, right? But here is what happens without inlining. I want to be able to show you that even if you put everything in other translation units, and even if you don't kind of have link time optimization, you're still gonna get close that is as small as this. But how could I convince you that this code is zero overhead? I mean, you're not reading this code right now and understanding it, right? Even though it looks small. I want to run a comparison, okay? Here is a standard practice that is out there, which is used, and we call this like outcome. I chose to use the experimental version because I got just better assembly. I didn't want to be mean, but this is like getting better assembly than the non-experimental version, so really good job there by Neil. So here is the code that we're using. There is just a small difference because in the outcome, we have to use this system error too. And by the way, all this boilerplate above is just making sure that we get the best possible assembly. If you know any way to get better assembly in outcome, just let me know because I think this is the best way. And what is the comparison? There is your comparison. So on the left side is the throwing type that we just implemented today, and the right-hand side is the outcome. The difference is not coming from coroutine versus non-coroutine. The difference is only coming from the exit condition that I showed. So if you implement the exit condition in one case, so you could get a fewer instructions when you do this propagation. So there's one fewer instruction in each of the uses of the exit condition or the variant type that outcome uses. Okay? So what about the integer divide equals? I just showed you only the integer divide. Maybe the integer divide equals is worse, right? So here I'm using a little bit of extension by outcome that is doing like expression statements in C++, and this is non-standard, but I just wanted to kind of show a nice syntax rather than splitting this to multiple lines. The same result will be there, and you can see that even though you can't say anything about this assembly, maybe the right side is faster. Just looking at the left side and seeing the difference in the amount of instructions is hinting us that maybe we really hit the zero overhead point. I mean, look at this. It's just like how many instructions are there? 31 instructions. So I think this is convincing. But what about all this meta-programming, try-catch kind of std visit kind of thing, right? Maybe this is generating super bad assembly. So here's the comparison for that. Oh, by the way, I just want to make a comment here. The reason I'm comparing here the addresses is just to be able to get to the same level of performance. There is actually an like comparison operator right there, and I wanted to make sure that comparing the addresses is really faster. And in my library I rely on like conforming ODR, so that's why I bothered to check the addresses. But if you don't have conforming ODR and you wanna you could implement like a comparison like this instead of doing like an address comparison. Here it's all behind the try catch, but you could do that. And the assembly is very similar. I have, in this case, just 2 more instructions. I haven't deep dived it to understand where the 2 extra instructions coming from, but this is comparable. I think maybe it's a result of having to support both dynamic and static exceptions. So I support both of them. So maybe the instructions are coming from this. So here is a summary of what we achieved. I think I convinced you that we achieved zero overhead. I also showed that this code is relatively freestanding. There is also, if you want to see afterwards, and I will make sure to upload it, like just the compile flags that they used. All failure paths are visible. Okay, so if somebody told you at work, hey, I don't like exceptions because I can't see the failure paths, here you have to type co-await. And if you don't, you get a compiler error. So this time you know where you're failing. What is still not perfect? So the co-await is still also a disadvantage because it is something extra we need to type. And of course, we are heavily relying on optimization. So if you have a bad compiler, you're not gonna get this code. I used the Clang 12 for the rest of the talk. For the entire talk, this is what I used. Remember this slide? So what does the new code look like? Here's the new code, and here are the differences. This is less than 10, you can check. This is less than 10 changes, and the difference is that the right-hand side code is freestanding, can run on stoves, and it just looks very similar in syntax to the left-hand side. It's just extremely more kind of portable if you discount the C++20 requirement. Okay, so what should we do now? Let's see how much time we have. About 11 minutes. So I want to show one kind of thing before I move to the Q&A. And it's here. And this is like somebody asked me before the talk, hey, it was just unrelated talk. He said, I really want to have this stack traces, and there is a stack trace proposal for C++. So as it turns out, the coroutines are really providing us the very nice tools, the very nice hooks all over the place. And it turns out you could implement stack trace with that. And I'm going to show a POC, and not just, don't have the entire code, but you do get stack trace. So just take a look. Here, just executing it. It returns 1 because, just pay attention here, this 4 divided by 2 equals 2. So it gets to the return 1 right here. Okay. So what happens if I will change it? Let me change it. Let's just have 3, right? Now we're expecting to just fail because 4 divided by 3 is not an integer. Let's compile it. Let's execute it. And you can see this stack trace. Let me just make it bigger. Stack trace, right there. How did I do it? So don't expect a full implementation, but you can definitely expect a POC here. So just take a look. Oh, this is terrible color scheme. I just used it for the projector. I think this is like, can see really well. This one is the one I need. And of course, libc++ doesn't have source location, so forgive me. This is just like for the talk here. And I really need to show you this yield value function. How do people do live coding in conferences? Yield. Oh, I need the suspend. I need the await suspend. I just forgot it. Okay. Here's the await suspend. And you can see this await suspend is getting like, let me just make it larger. It's getting like this source location default argument. And this is what gets us to the ability to just use a std_cout. So it gets passed by the compiler every time you fail, because suspend is only when you fail. So only when we fail shall we get this stack trace. And this is in two places. This is one in this place, and there is another one in the other place of the awaitable type. So they do the same thing. This is the right one? I don't know. Never mind. It's the same code, so trust me on that. And we really don't want to print it right here. We want to store this stack trace information efficiently somewhere, and then to be able to display it anytime we fail. So there is no runtime cost for the success path. It is only on the failure path. So what do we do now? We have like 9 minutes, right? So we need to leave some time for Q&A. So co-return, thank you. Any questions? Yes?
How will generators affect the drawing points if they ever get into the standard library, or is this strong code will also be part of the standard library as well?
So the question was, how will generators that are possibly getting into the standard library affect this code? It's a very good question, which I haven't thought about yet, because when I implemented this, it was like just, I think, a few weeks before the conference where I achieved this much like improvement. But your point is valid, because we need to think how we would just composite this code together with other coroutines. And I think because I get a lot of confidence from working with coroutines, look, I just able to get the stack trace. So I get the confidence that this is possibly doable. But I don't have a definite answer right now. Any more questions? Yes?
So does this still properly unwind the stack like normal exceptions would?
The question was, does this unwind the stack like normal exceptions do? And the answer is that exceptions usually implemented by some kind of table-based implementation and require an unwind library. And the answer is here, we're just really using return values. We're not using the unwind library, and we're not using any library for that matter. We're just using standard C++ headers, and it's all going according to the coroutine kind of protocol design that gets you to return or suspend, and everything that we did in this talk is kind of taking care of the propagation.
So the destructors don't get called?
No, destructors get called. The question was whether destructors get called. The destructors get called because every time you execute the coroutine, remember initial and final suspend are returning suspend never, and every time you suspend, it's causing a destroy. And the destroy is making sure you actually call the destructors. And as we saw, it gets inline. So it's gonna be just like a function that calls the destructors in the end. Like if you yield or if you return, it will call the destructors.
But
Yeah.
for that to work, all the functions in between where the error happens and where you handle it have to be coroutines that return the throwing.
Yeah, if you want to do the comment was that every time you want to do the automatic propagation, you need to return a throwing of some type. I think this is similar to other proposals that I've seen. I mean, this is not a proposal, this is just a library. But proposals that do exceptions other way, you also need to do some annotation to the function to make it like propagate. So this kind of thing I think is reasonable, but good comment there. Yes?
you actually work with classes, class generators, or class? If your return type was like a vector or something that you wanted to return, but if something fails when you create that vector, would that be possible using your drawing library?
You can return the question was if you would use like let me see if I got it right. If the return type is throwing off another coroutine type, that's what you mean?
No, I'm saying like basically your future type is a vector or.
I see. So if the return value is a throwing off vector of cars, that's what you're asking. So what would happen? Vector of anything, right. So vector has a move constructor. So anytime you co-wait, you actually, I don't think you need a move constructor. I will need to think about that offline, but it's gonna work. I mean, I tried it with like containers, with like stuff that is not trivially constructible, destructible, all these kind of things, and it works. I don't know if there is a requirement to have a move constructor. Probably there is, but I mean, most types today have move constructors, so I'm not concerned about it. Any more questions? Yeah.
Just was curious, can you also use a little bit of concepts inside of this to make it easier for verifying your types that are acceptable in your templates?
This is a good comment. The comment was, like, can we just put more concepts, like deploy more concepts into the implementation of the library? Now, I didn't show a lot of the implementation of the library because I wanted to just fit everything on a slide. A lot of it already receives some kind of, I don't have like the explicit concept keyword, but I do have like requires stuff. And it's a right comment. I feel like I should polish this implementation more, you know, and maybe provide better documentation. But just if you go to this GitHub right there, it's gonna have plenty of examples and like documentation. It's not like fully, don't expect like CPP reference kind of documentation, but it does have what you need to get started. Another person, yeah.
What happens if one coroutine calls the other? How do you propagate the exceptions between the two?
So
The boilerplate at both sides?
okay, so the question was, what happens if you have multiple coroutines calling each other? So in the talk right here, we showed like integer divide equals that is calling integer divide, and integer divide equals is being called from the main function. So as you could see, this is like more than two, and we didn't have to do any boilerplate. We just need to put co-wait every time we call to the function, it will work, and it will propagate. Convincing? Yeah, okay.
So if you have a runtime exception that you wanted to like have each of your lines that only work with you know parts of that drive type, or you know each of the drive types, but you want to have your base type to work with more of a generalized version, is that possible using your library, or because I don't think that that's really possible using standard C++. Of course, I can be wrong.
Yeah, I think I may have a slide on that, but let me see if I can get there. It was a good question. The question was, how do you support with standard C++ this kind of checking for derived types in runtime, right?
Well, no, I was actually saying like you wanted to use your exception handling so that you can kind of keep your code in general, but like you know, derived type might have specific information. So let's say like you were saying like intra or timing. If you wanted to kind of log your exception, but you have part of it that's general to your derived type or derived exception, and part of that that's specific.
Let me stop you right there. Just bump into me in the hallway. This sounds like very complicated for now, but definitely let's speak after. Any more questions? I think the last question. Okay, so just wanted to finish the Q&A with one kind of thing for you to kind of remember, you know? So if you want to remember something from this talk, here is the thing you want to remember. So I wanted you to kind of feel what I feel at the end of this talk, and this is that C++ is the language that provides tools to the programmers so that the programmers can invite what was unimagined by the authors. Thank you so much.